Hello, YouTube. I know why you're here. You want to talk about gravity for 1 to 2 hours. More than anything in the world. Good thing. That's what we're gonna do. Um, there's a lot going on here. Honestly, this should be broken up into like 3 lessons, 4 lessons, or something. But I think I'm just gonna go through it all, and so it's all in one spot. In particular, we're going to talk about the gravity equation. We're going to try to think of like every possible ramification from that and use that to go from there, I guess. Ideally, end of this, you should be able to find and derive escape velocities, and this is not in the right order. Find and derive escape velocities, derive the orbital period of an object, find and derive the period for an object that's following through the Earth, which is a weird statement, model the motion of an object that goes between different paths on an orbit using energy, and like goes up or down to different orbits. In particular, also, we're going to be talking about how to model the energy of an object that is in orbit, as well as derive sorry, that's already on there. And just kind of find out how much gravity is on something. That's sort of the basis of all of it, and I don't know, it was a little easy, so I like forgot that it needed to be a thing you need to do. I am not even going to try to draw this stuff because it's a lot, and we're going to just skip straight to doing a bunch of derivations on paper. The really big takeaways from this are going to be both the equations and how to get them. So I'll try to walk back through the step-by-step process as we go. Really pay attention to the end results. Really pay attention to how we got there, because sometimes you'll be asked to rederive them. Most of them don't show up on the equation sheet. So gravity. Newton's universal law of gravitation is that the force of gravity from an object will equal capital G, which is the gravitation constant of the universe, times the mass of the first object, times the mass of the second object, divided by the distance between those two objects squared. And that's it. Capital G is a fixed constant. It is, 6 times 10 to the, I want to say 23rd. Oh, I really should have looked this up before I started. Yeah, I think it's 6 times 10 to the 23rd, but now that I think about it again, I'm pretty sure that's wrong. It's a number, and it's a fixed number in Newton kilograms squared per meter squared. That one is on the equation sheet, and thankfully you can just look that up. I'm gonna need that for all the examples. Okay. 6 times 10 to the negative 11th. Not even close. I believe that's like mass of the Earth. So that constant is basically representing how strong gravity is in the universe. If that number was bigger, then you would get more gravity than we currently have attracting everything. If that number was smaller, you'd get less. So any two objects in the universe, the force that's between them on either object is going to be equal to this. So let's say you've got mass 1. There'll be a force of gravity going towards mass 2, which will have the same force of gravity going back. This part tends to be a little counterintuitive. Newton's third law continues to apply even to gravity. So the moon pulls the Earth just as much as the Earth pulls the moon. Yes. You can do this by, you can find the net force from this by adding up multiple forces. This gets notoriously annoying. when you have a bunch of different things like orbiting each other, or a bunch of different things that are experiencing gravity with each other. So you're probably and hopefully not going to have to do too much of that, but it is a thing that could potentially show up. I think that's pretty much it for that part. So this is our force equation that we're going to be using. I guess a couple notable features. Both masses matter. So if the mass of one object doubles, then the force applied doubles. If the mass of both objects double, then the force applied quadruples, because you've got times 2 and times 2 in the numerator. In the denominator, you've got r squared. So if r squared gets bigger, then it's kind of the other way around, where if r doubles, you're twice as far away. That exponent means that your attractive force gets cut in a quarter, because the squared sort of compounds that and makes it matter more than it otherwise would. All right, so I think that's pretty much that there for that. So this equation is going to be the basis of a lot of what we do. Not quite all of it, but a lot of it. So the next thing I want to do is start thinking about something a little bit weird, and think about the amount of force that's going to be on an object that's in the center of a planet. And for this, our first basic piece of information is the hollow shell theorem, which states that for any given point within a spherical hollow shell, you'll get this section, which is pulling the object to the left. You'll get this section, which is pulling the object to the right. Now it's weird because this little chunk is closer in to the object. And so this one creates more force per unit mass because the radius or the distance is much smaller. But if we come over here, this side is less force per mass unit, but there's more of it. And so those two factors wind up completely and totally canceling out. And what you wind up with is a situation where neither side actually winds up pulling the dot more than the other, and all of the forces on it completely cancel. So if we were to tunnel through the Earth, as we got closer to the center, we'd have less and less mass above us, or below us, and the mass that was above us wouldn't be putting a force of gravity on us because it's a hollow sphere. So if we make one really big assumption here, I guess two really big assumptions, the first of which that the Earth is a sphere, and the second of which is that the Earth has a uniform mass density. Then if we wanted to find the force as we traveled through the center, then what we could do is think about what's causing our force of gravity. Well, our net force is gravity. So capital G, our mass times the mass of the Earth that is below us, divided by where we are compared to the center of the Earth squared. So if we're at this point here, this is R, and this is our enclosed mass. or a mass that's below us. So the problem is, as r changes, the amount of mass that's below us changes as well. And so if we want to try to model how much force there is here, we're going to have to do it in such a way that we're including and being careful about how much mass is below us. So to do that, what we can do is say that our force, that our mass that's enclosed, if we have a uniform mass density divided by the volume that's below us, will need to equal the total mass of the Earth divided by the total volume of the Earth. Because our density for the remaining section needs to equal our density for the beginning section, for the entire thing. If we plug in for the volume of a sphere, we'll have 4/3 pi r cubed, where lowercase r is where we are now, which will give us the volume that's below us, and uppercase r is the volume of the actual Earth. So if we take these two things and we set it up so that we can solve for the mass that's below the Earth, we'll be multiplying by 4/3 pi lowercase r to the third. 4/3 pi lowercase r to the third. Our 4/3 pi cancel from both sides. And what we're left with is that our mass that's below us will equal the mass of the Earth times the radius cubed, our location cubed divided by the radius of the Earth cubed. From here, if we take this and plug this back into our force from gravity equation, the amount of force that's on us will need to equal g m1, so our mass, times the mass of the Earth times the location we're at cubed divided by the location we're at squared times the radius of the Earth cubed. Now, these two wind up canceling out to some extent. We've got r third to the third divided by lowercase r cubed. And so that simplifies a little bit to g, I'm going to actually write it as m1g, mass of the Earth divided by the radius of the Earth to the third times r. And that will equal our mass times our acceleration. And this, to me, is pretty interesting. Relevant if we have a positive position, as in we are above the center of the Earth, gravity will be pulling us down. If we have a negative position, if we are below the center of the Earth in our drawing, gravity will be pulling us up. So I need to go back through all this. Gravity will be negative, gravity will be negative, gravity will be negative. This is interesting because all these are constants. And this is our location. And this is our second time derivative of our location. And if you just watched the simple harmonic motion video, this should be throwing off some alarm bells in your head. Because what this situation is the same as if it was a spring. And so, with a spring constant equal to this information. So if an object is dropped in a straight tunnel through the surface of the Earth, it'll start at the top, and then fall all the way down to the middle, and then speed up in the process, and then fall all the way from the middle down to the bottom, and slow down in the process until it reaches the other side, just as if it were attached to an obscenely long ideal spring. No, there's the whole problem of all the other stuff in the Earth getting attracted to the center of the Earth via gravity. So while there wouldn't be a force of gravity on you, there'd be the pressure of the entire weight of the rest of the Earth pulling down towards and squishing you. But, aside from that, it'd be a really great way to get from one place to another. Again, aside from that. So if we set up our simple harmonic oscillator equations, and we'll get something where, once again, this constant that's out front is going to be the square root of the thing that's in front will be what's related to our it will be what's inside our trig functions. So our x function will be such that the radius of the Earth, which is our maximum x amplitude away from the center, times our cosine of the square root of g me over capital R to the third times our time will be our x location. For our velocity, we'll have r root g m Earth over radius of the Earth cubed times the sine of sine of r constant divided by r cubed times our time. And for our acceleration, we'll have that negative r g mass of Earth divided by r cubed, our r's drop, times the cosine of g mass of Earth over r square rooted times our time. When we do this, we can also get a period, just the same way we did the other. This thing, when we plug in our period, needs to equal 2 pi. So 2 pi equals root g mass of Earth divided by r to the third times our period. So if we invert this and multiply by r to the third over g mass of the Earth square rooted, r to the third over g mass of the Earth, we'll get that our period for this function gets longer when we have a higher radius planet and shorter when we have a heavier planet. Because when we have a heavier planet, there's more gravity pulling us towards the center. And when we have a larger radius planet, we have less force pulling us towards the center. So I'm going to level with you. These probably won't show up on the AP exam. It's kind of one of those weird things that keeps getting brought up in a bunch of different physics books because it's such a weird, neat thing that it happens. And so physics teachers, hi, hello, keep assuming that people want to hear about it and figure it out. And are like, oh, it's such a good problem. But it's kind of convoluted, right? You have to go through it and figure out how you can turn the enclosed mass and model that as a function. You have to have it so that you have a constant density for your planet all the way through. And neither of those things really wind up being the case. The first one's just annoying. The second one, wind up being the case ever. And so you probably won't see this on the AP exam, but that style of thinking, that idea of how can I model this situation and how can I use simple harmonic motion to model it once the equation form shows up, that type of thing will actually absolutely potentially be on the exam, and it's something that you should be looking out for. All right. Next concept. Let's say that we've got something that's orbiting. So if we've got like a satellite that's going around the Earth. Well, few basic ideas that are going to be coming up here. The first of which is that our angular frequency our angular velocity is going to be related to the amount of time it takes us to go in one complete circle around the Earth. One complete circle is 2 pi. So our angular frequency is going to be equal to the full 2 pi divided by the time it takes to go around the full 2 pi, or t. You could also conceptualize this as thinking of it as your tangential velocity will equal 2 pi times the distance that you need to travel, the circumference, divided by the period or the amount of time that it'll take. These two ideas are going to be things that are useful occasionally throughout the processes that we're going to talk about. The second idea that's useful throughout the processes that we're going to be talking about, and I would make sure that you know, understand, and remember this. They're just coming from distance divided by time, or angular distance divided by time, because a full circle is either the circumference, distance here, or the full circle is 2 pi radians, distance here. The time for that full circle is the period of one complete cycle of rotation. Great. So for our next idea that can come up is that if something's moving in a circle, the centripetal acceleration that it has will be equal to the centripetal force, so mv squared over r. Well, that centripetal force, if it's gravity, is going to need to be equal to gmm over r squared is equal mv squared over r. Those two masses will drop. And so you can find this relationship between your tangential velocity and how far away you are from the center of the object if you know those pieces of information. And you also need to know the mass of the object that you're orbiting around. So this is sort of our second key concept that's going to keep coming up. The last thing I should have honestly done before I started talking about orbiting, which is potential energy. Specifically off the surface of a planet, the equation we've been using so far is a good approximation, and I'm not going to do it here, but it's actually a really worthwhile exercise to try to derive our old equation for potential energy, and double check that when your distance is, the difference between your two distances is very small, that you do actually get out pretty much a linear function. But to start with, what I want to figure out is the potential energy off the surface of a planet. The first thing that you need to do when you're finding potential energy is you need to figure out what location should be your zero location. You could say that your zero location is the inside of the object. The problem is when r is 0, your force equation freaks out because your force equation becomes non-defined. So picking that as your location where you have no potential energy kind of doesn't work. So instead, we need to pick another arbitrary point to have a location of 0. You could theoretically pick anywhere, but kind of the only thing that makes any sense consistently, if we're looking for one consistent equation that just works, is if we pick another point that's always going to consistently be available. And that's a location that's infinitely far away. This is going to lead to something a little bit weird because we can get negative energy. It's fine, it's not a vector, it just means that you've got an energy debt or an energy well that you would need to escape in order for you not to eventually get sucked back in towards the center of the planet in some way, shape, or fashion, or be orbiting the planet. And so one of the key ideas here is we're going to choose to be setting things up such that our potential energy equals 0 or approaches 0 when our distance away from the center is infinitely large. In order to do that, our potential energy will wind up being negative, conceptually. Because we need to have our energy decrease as we get closer to the center, because something that we drop from somewhere closer to the center of the planet will fall less than something that's further away from the center of the planet, and so the total effect will be that it'll wind up going slower. Which means it had less energy stored up as potential. Potential energy is related to force via thinking about work. If gravity is going to be doing work, and that's the thing that's giving this thing potential energy, what we can do is we can find the work that gravity does going from a certain distance away from the center all the way out to infinitely far away. And to do that, we just need to take the force of gravity and take the dot product with a tiny little distance away and move it up by a tiny little distance and add up all of the little chunks of energy and all of the little chunks of work that our force is doing as we move along that location. Well, the force of gravity dotted with dr is going to be equal to the force of gravity times dr times the cosine of the angle between those two things. Well, at any given point, dr is going to be going away from the center. And at any given point, the force of gravity is going to be going towards the center. So the angle between them is equal to 180 degrees. And that means that our cosine is going to be -1. And so from here on out, when gravity is doing work, the work that gravity winds up doing in this case is going to be negative. Okay, well, let's just plug in the gravity equation. Well, our gravity equation is gmm over r squared multiplied by dr. We're going to be going from r to r from r to infinity, but in order for that to happen, we have to take our integral first. So our integral is going to be negative r to the second integrated. Negative r to the second is going to be r to the negative first times -1. So negative gmm over r evaluated from r to infinity. At this point, I don't know why I keep doing that. At this point, our two negatives have dropped. And we're back to getting positive work done by gravity. Well, actually plugging in the stuff that we've evaluated, if we go from infinity as our radius, we're dividing by infinity, and so our potential energy when we're infinitely far away is 0, just like we conceptually set it up. We're then going to subtract and plug in r. gmm over r. And once again, we're back to negative. And so what that tells us is that the potential energy that gravity gives an object is going to be equal to negative gmm over r, or m1 and m2 over r. And this is one of our core equations here. So our potential energy that the object has is going to be equal to gmm over r, while our force from gravity is going to be gmm over r squared. The potential energy is also going to be negative. So if you look at a graph of potential energy, that potential energy will start when you're at the radius of a planet at a big negative number, and then as you get further away from the planet's got less of an energy well trapping you inside of it, because the planet is going to pull you back towards the planet if you let go of the object. And in particular, if you remember from earlier, the negative derivative of our potential with respect to where we are will need to equal our force. So it works like a marble on a hill. If we place a marble here, it'll get rolled back towards the surface of the planet until it reaches the surface of the planet. This isn't an asymptote, this just cuts off. In theory, this would get infinitely large as we get closer and closer and closer to the center of the planet, without ever being able to actually reach the center of the planet. Or I guess not infinitely large, infinitely small. And we'd have an infinite amount of energy debt the closer we got. Sorry, I'm trying to figure out if that is actually infinite or if that is an asymptote. But yeah, it is. It gets infinitely negative. Because we're getting to a situation where our objects are so impossibly close together that you have the entire mass of a planet condensed into this tiny little point. If we combine that though with our earlier understanding, once we go past the radius, this isn't actually how it's going to work. The potential energy inside of the planet is going to linearly decrease like a spring until it gets to 0 in the center. So you'll actually have this really weird thing where you've got this linear function where you gradually get slightly more and more and more potential energy as you go. More and more negative potential energy as you go. And then as you get further away from this, until you reach the surface, and then as you get further from the surface, you'll get more and more and more, or less and less and less negative potential energy until you eventually escape. Let's go with that concept of escape. Because my potential energy is negative, in order for us to leave, we need to have enough energy, mechanical energy, that we'll be able to get infinitely far away without reaching up to part of this hill, stopping, and getting pulled back down and in. Now, that will happen when we either have no total mechanical energy because we've undone all of our negative potential energy, or positive mechanical energy. So what that'll look like is that our mechanical energy, which will need to be equal to our potential energy plus our kinetic energy, will need to be equal to 0 if we have enough kinetic energy to escape. This is the core idea that we can use to figure out what the escape velocity is. Escape velocity is how fast we would need to go in order for our object to leave Earth orbit and actually leave Earth orbit forever. Or whatever other orbit. You can find escape velocity for the sun, you can find escape velocity for Jupiter, you can find the escape velocity for any star or any planet or any situation. The weird thing with black holes is that the escape velocity from a black hole is faster than the speed of light, and so nothing can escape a black hole because nothing can go faster than the speed of light, just as a brief little thing from that, beyond the scope of this test. But neat. As always. Yeah. actually finding escape velocity. So our potential energy here is going to be negative gmm over r. Our kinetic energy is going to be 1/2 mv tangential squared, or the escape velocity squared. That will need to equal 0. That's pretty much the entire process. There's mass in every term and it equals 0, so we can get rid of the mass of our object that's trying to escape. So weirdly enough, how fast you have to go in order to get out of Earth's clutches is completely independent of what your mass is. And from there, all we have to do is add gm over r to both sides plus gm over r. And that'll give us 1/2 escape velocity squared is equal to gm over r. Multiply each side by 2, multiply each side by 2, square root, and we'll get that our escape velocity, or the speed that we need to be going in order to leave orbit of a planet, is equal to 2 times the gravity constant times the mass of that planet divided by the location we're at away from that planet. So the further away you are from the planet when you start, the better off you are. Cool. Also not on the equation sheet. The idea for escape velocity is one that could potentially come up. It's kind of weird because gravity is just like so weird and broad, and there's so many of these weird little interactions that it's like a really good thing for them to pull from open response questions, but there's also a pretty limited number of ways they can do it. And it's also really hard. And it also is like hard to get partial credit on it. For this one, you either know the trick that you're trying to make the energy equal 0 or you don't. And if you don't know the trick that you're trying to make the energy equal 0, you can't even really start the problem. So it's hard for them to, like, in good conscience, assign it as an open response question on the test when there's only 3 open response questions. They'll do it, but they do it once every few years instead of, like, every year. Like, there's always one question that's just rotation on every exam every year. So, like, 1/3 of the open response is rotation every time. Yeah. All right. We've derived escape velocity. Next step. Let's think about the energy while an object is in orbit instead of an object that's trying to leave orbit. So if an object is in orbit, it's going to have an orbital radius, and it's going to be going at some velocity, and that's pretty much it. So let's find the mechanical energy for an object in orbit in terms of its velocity. In terms of the radius of the orbit and the mass of the object that it's orbiting, which I'm just going to start calling capital M. Lowercase m is the smaller mass, capital M is the bigger mass. Saves you from writing some subscripts, helps out a little bit as far as like effort and writing. So to do that, we want to start thinking about our potential and our kinetic. Well, our potential is negative g m for r. Our kinetic is 1/2 mv squared, lowercase m, v squared. Taking that and putting it into an equation to figure out what our mechanical is going to be, our mechanical is going to be negative g m over r plus 1/2 mv squared. V squared is kind of an interesting one, because if we think back a sec, for me that really reminds me about the centripetal force. The force that's pulling this thing in towards the center is going to be gravity. But that's also going to be the centripetal force. So Gm, capital M over R squared is going to need to equal mass times our tangential velocity squared divided by our radius. Those two r's are going to drop, the lowercase m's are going to drop, and we'll get an equivalency of Vt squared with our centripetal force. If I take this and I plug it back in over here, negative G mm over r, which is our potential energy, plus 1/2 mass times this term. So G m over r with a 2 on the bottom. What this means is that for any object in orbit, the potential energy will equal double the kinetic energy, but negative. This is one of the other really big takeaways. No matter what object you have in orbit, and actually I should be careful, this should be, before I forget, this should be lowercase r because it's not representing the radius of a fixed radius or a constant. Typically uppercase r is reserved for constants. Lowercase r represents wherever we are in the orbit or the location. So I really should have lowercase r here instead of uppercase r. Is it a huge deal? No. Can you leave it as uppercase r? Absolutely. Just a thing to be mindful of, because sometimes you get situations like the one that I think we've already ran into, where we had to be careful about which was uppercase r and which was lowercase r with the whole period problem. Sorry, so back to the actual point here. For any object that's in orbit, your potential energy will be negative and twice as big as your kinetic energy. And that will actually always be true. The only thing that we assumed in this case was that our centripetal force would be related to our tangential velocity, which is always true. Otherwise, we won't be going in a circular orbit. If it's in an elliptical orbit, this actually still works. You just have to use your semi-major axis, which is the distance from the foci to the smallest orbit point, I think. No, not from the, oh gosh, I haven't done that in a hot minute. But you can use your semi-major axis instead of r and it still works. The ideas of it are going to be the same either way. So this will also equal negative Gmm over 2r. That's also one that you should try to have and know, which is that your mechanical energy is going to be equal to Gmm over 2r. They literally asked about 15 years ago now, they literally asked an open response question on the AP exam that was just derive that. And that was, I think, 1/3 of the points on the problem. So what, 1/3 of 1/3 is 1/9, and it's 1/9 of 1/2. So 1/18 of the exam's total points. So 6-ish, 5-ish points of the entire exam out of 100 were knowing how to do this derivation. If you know it, if it makes sense, it's really just 2 lines, 1/3 of a page. But there's a few different things to keep track of. Briefly going through those again, we need to know that the potential energy equation can be used. We need to know that the kinetic energy equation still works. We need to know that their centripetal force is gravity, Gmm over r squared, and we need to know that our centripetal force is going to be something that we can actually solve for using mv squared over r, setting that equal to our centripetal force equation. then we can just plug that in for velocity squared and get our final answer. So that's pretty much it for kinetic energy, for mechanical energy. One other quick thing I do want to highlight here, though. You get less mechanical energy the further you are from the center. So as the object gets progressively further out, it's got, less negative mechanical energy. So in order to go into a wider orbit, you actually need to give the object more energy, and to go into a tighter orbit, you need to take energy away from the object. This little equation here also tells us something interesting, which is that our velocity squared will need to be related to gm over r. And so as our orbital radius gets bigger, our object actually winds up, when r gets bigger, our tangential velocity for our object winds up getting smaller via the way that the force ratios work out. Because we have less force available, and so we need to be going slower. Great. Talked about mechanical energy, we need to talk about orbital period. And then we can do the example problems. Orbital period. So let's say we're trying to figure out how long it takes for our object to actually go in a circle. Great. Well, we can start using that equation that we just had for the last one, which is that our net centripetal force will need to equal our gravity, gmm over r squared, and it will also need to equal mv squared over r. Well, v squared, if we're trying to figure out our period, our speed that we go in the circle is going to be related to how long it takes us to go into the circle. Our velocity will equal our distance over our time. Our distance we need to go for one complete revolution is 2 pi r, or the circumference of the circle. The time it takes will be the period. So we can take this and plug it in over here. When we do that, what we'll get is that gmm over r squared will equal m times 2 squared pi squared over r to the third. Nope. R to the third over our period squared, which is also being divided by r. At this point, r drops with r squared up at the top. And so if we solve this from here, our mass drops, and we'll get a relationship where multiplying each side by our period squared and dividing each side by gm and multiplying each side by r squared, gm r squared, the period squared will only depend on 4 pi squared, that one doesn't change, divided by capital G, capital M, the mass of the objects we're orbiting, and the orbital distance away from the object to the third, because we'll have r squared times r. What that means is, as your orbital distance increases, your period will also increase. So your orbital period, or your year length, will also increase. Planets that are closer into the sun have a shorter year length. Planets that are further from the sun will have a longer year length. The ratios for that are really, really, really weird because of the squared into the third. So like if your orbital period radius doubles, then your period squared goes up by a factor of 8, so your period will be root 8 times as long, which is weird. Yep. Time for examples. Time for takeaways. Just kidding. So our big takeaways from all of that are as follows. The equations and the process for getting them are the most important part. If you could follow those equation derivations and you remember the equations, that's going to be a huge help. I would strongly recommend finding a way to look at past AP exams and do practice problems from those past AP exams and just make a list of the problems that you see showing up and what types of stuff you're going to be expected to be able to do with gravity, and just make sure you know how to do it. It's kind of this weird thing where there's a lot of stuff you can do with it, and it's just kind of taking and combining those ideas that we just talked about in new ways. Because most of the equations that we just figured out aren't on the equation sheet, kind of just got to know them. So one of the core concepts from that is the relationship between kinetic and potential energy, where when you're in a circular orbit, where you've got twice as much but negative potential energy as you do kinetic energy while you're orbiting. The second really big one was that our tunnel through a planet will behave like a simple harmonic oscillator, because you have less force on the object as you go towards the center of the planet, and more force on the object as you go towards the surface of the planet. And then less force again as you leave the surface of the planet. So the biggest force from gravity on you from the planet will actually be directly on the surface of that planet, unless it doesn't have a uniform mass distribution, and then things can get weird. So any real planet, things can get weird. But eventually, as you tunnel towards the center, something similar to that will wind up happening. As far as potential energy from gravity goes, it is going to be negative, and you are going to be setting it so that the 0 point is when you're infinitely far away. So you're getting a less negative number or more positive number by getting closer to being 0 net potential energy by being far away. And what that does is it means that you're effectively trapped in this well of getting sucked back in towards the planet by gravity unless you're sufficiently far away and moving fast enough that you have a total mechanical energy greater than 0. So that means that your escape velocity, or the velocity required in order to actually leave a planet's orbital influence, is going to be whatever velocity gives you enough energy to have a remaining mechanical energy. That is positive or 0. The escape velocity, or the minimum velocity, is at exactly 0. Examples. How am I doing on real life time? Oh, not good. Not good at all. That explains a lot. So, find g, the acceleration constant, on a planet that has a radius of 1/2 of that of Earth, but a mass that is 3/4 that of Earth. First one's not too bad, it's just going to wind up being proportionality. And this will wind up sort of being the case for a lot of these problems, is that the hard part was doing all of the thinking and figuring out how that relates to things. Once we've done that once, it's not too bad to do it. It's just that there's a lot to juggle and keep track of okay, but which concepts work for this one that I'm doing now and which ones don't. So to do this, our force of gravity is going to be equal to gmm over r squared. Something that I didn't talk about enough, because force is equal to mass times acceleration, the acceleration that will be caused by gravity is actually independent of the mass of your second object. The acceleration of your second object will, if gravity is the only force acting on it, will always just be equal to gm over r squared. This value and this idea is something called a force field, where the field for a force is the amount of force that you would have on an object per unit, in this case mass. For electricity, it's per unit charge. So when you're finding a force field, or when you're finding the acceleration, in this case what winds up being the acceleration, you can completely ignore the mass of the object that's being accelerated. So when we're doing this here, our acceleration will be proportional to capital G m over r squared. Well, g is a constant. So if we do our old tricks with proportionality, our acceleration, if we've got a radius that's 1/2 as big and a mass that is 3/4 as big, now that I've got the problem copied down and gone through the basics of what we're doing, our acceleration will be 3/4 for the mass of the thing that's, for the mass of the planet being 3/4 as big, and 1/2 on the bottom squared. That 1/2 squared will become 1/4. So we've got 3/4 over 1/4, which is 3. So our acceleration will be 3 times as big if we manage to somehow get a planet that is half the radius, which means it's going to have 1/4 the volume, or no, 1/2 the radius means 1/8 the volume, because the radius gets cubed. But despite having 1/8 the volume, we only lose 1/4 of our mass, which means that our object, this planet, is much more dense than Earth. But if that wound up happening, we would wind up with acceleration from gravity that was 3 times as big. That's a thing that I've seen like 3 or 4 times on past multiple choice. So that style of question can show up, and it can be a multiple choice problem. Just be ready to do basic proportionality stuff and you should be fine. Next question. Find the velocity and mechanical energy for a satellite of orbital radius r around a planet of mass m in terms of givens. I think we've already done part A. For part A for this one, the mechanical energy is going to be negative gmm over r squared, and our velocity is going to be, just using our basic premise of centripetal motion, gm over r will be equal to velocity squared. So our velocity will be equal to the root of this. So we've done part A. You couldn't see any of that. If we want to double the radius of the orbit, how much work would we do? Would it be negative work, positive work? Would the satellite be going faster or slower? Okay. Taking advantage of the fact that we've already done some of this, for A, our answer is that this is our mechanical energy, because it's in terms of the givens. We would need to know the mass of the smaller object, because the energy will depend on the mass of the smaller object. So my bad for not including that in the problem. And then our velocity equation will be based heavily on this concept here, using our centripetal acceleration. So for our energy, our mechanical energy will be negative g mm over r. Our velocity will be based on our centripetal force equation. So g mm over r will equal mv squared over r squared. Solving for v, cancel out r, cancel out m. V squared will be equal to g m over r. Square root both sides, and we're done. our velocity will be equal to the root of gm over r. For part B, we're trying to find how much work is required to double our radius. And then we're being asked, will our velocity be faster or slower? God, I still feel like I'm doing something wrong for that. Oh, well. So, yeah, because you're supposed to slow down to go into a tighter orbit and speed up to go into a wider orbit. Oh, well. Okay. So, if we're looking at the work that we're doing, our mechanical energy is going to, plus whatever work we do, will equal our mechanical energy at our second location. If we're doubling our radius, we're going from our mechanical energy from our first location, and that'll be proportional to 1 divided by our radius. If our radius doubles, what that means is that our mechanical energy will be 1/2 as big. But it's 1/2 of a negative number. So in order to get a less negative number or a more positive number, our work will be positive 1/2 of the mechanical energy at the first location, which is going to be positive gmm over r times 2. So we need to do positive work in order to go from a tighter orbit to a wider orbit. When we do this, our radius will increase. Because our orbital radius will double, our velocity will go down by a factor of 1 over the square root of 2. Or get 1 over square root of 2 times as big using proportionality. That still feels so wrong to me. Sorry, I there's something in the back of my head that's just screaming that, like, wider orbits, you go faster to hit a wider orbit, you go slower to hit a more narrow orbit. But I'm blanking on how that's possible given the math, so whatever. Problem 3. The moon is about 600 times further away compared to the radius of the Earth. So the distance from you to the center of the Earth is 600 times smaller than the distance from the moon to the center of the Earth. How fast would the moon be going if it dropped to the surface of the Earth in terms of the radius and mass of the Earth? So to do this one, all we pretty much have to do is think about our potential energy. The moon currently has potential and no kinetic if we're dropping it. It has a lot of kinetic as it stands because it's not dropping. that will need to equal the potential it has in the second location plus the kinetic it has in the second location. Well, the potential in the first location is going to be gmm over the first distance, which is 600 times the radius of the Earth. That will need to equal the potential in the second location, negative gmm over radius of the Earth, plus 1/2 mass of the moon times the velocity that the moon will be going squared. Mass of the moon drops, and all we have to do is add gm over re plus gm over re. That'll get us positive 599 gm over radius of the Earth. Over 600 times the radius of the Earth, which will be equal to 1/2 times our velocity squared. Multiply each side by 2, multiply each side by 2. Where I'm getting that from, by the way, is that this is equal to 600 over 600. So 600 over 600 minus 1 over 600 gives us 599 over 600. Which will give us 599 gm over radius of the Earth is equal to our velocity squared. Square root both sides, and we're done. Next one. Mass of the Earth is 6 times 10 to the 24th kilograms. The radius of the Earth is 6 times 10 to the 6 meters. What would the period be for a person that fell through a perfect hole drilled from one end of the Earth to the other? Thankfully, we've already done all the math out for this one. Our period, if we look at our earlier equations, is going to be equal to this is the problem with doing too many equations. Our period is going to be equal to I really hope I did that last one on the big camera instead of the small camera. Oops. Our period is going to be equal to 2 pi times the square root of r to the third over gme. So, looking at our values from the problem, we've got 2 pi times the square root of our radius from the Earth squared, which is 6 times 10 to the 6th to the third, divided by g, which is 6 times 10 to the negative 11th, times 6 times 10 to the 24th kilos for our mass. 10 to the third is going to get us 8 on the bottom, which is going to give us 10 to the third on the top, because, 6. So 10 to the fifth on the top. 10 to the fifth, 6 to the third divided by 2 sixes is going to be 6 times 10 to the third, fifth. 6 times 10 to the fifth is where I start busting out a calculator. So 2 pi six times 10 to the fifth equals 2 to the 0.5 times 2 times pi is going to get us 4,866 seconds, which, if we want to convert that into something a little more useful, if we divide that by 3,600, that'll get us hours, because there's 3,600 seconds in 1 hour. So dividing that by 3,000, 3,600. Our period to get us all the way from one part of the Earth to the other is 1.35 hours. Now this isn't the time from the one part of the Earth down to the other part of the Earth. It's the time from one part of the Earth to the other side of the Earth and back, because this is our full period, and it would only take half a period to go all the way through. For reference, the flight time from Boston to Hong Kong is 12 hours. So if you want to go exactly... Oh, sorry. I was like, there's no way that's right. The flight time is 20 hours. So cutting through the center of the Earth is shorter. We don't have to go as far. And it's also way, way faster because we go in impossibly fast time than if there was actually, or you'd hit terminal velocity way before that. But way faster if we drill a tunnel directly through the center of the Earth. In fact, it's 20 times faster. So just saying, if you want to save valuable fuel resources and valuable time, transporting people from one side of the globe to the other, we really should just be drilling a tunnel all the way through. This video is getting way too long. That's the last example problem. I do really recommend going over old practice exams, looking at answer keys for them, double checking that you know how to do the problems from them. That's really going to be your best bet. The examples I picked were sort of trying to cherry pick bits and pieces here and there from multiple choice, which is why some of them were so fast, and open response, which is why some of them were things that we covered more in the example, like less in the example problems and more in the derivations. So it is this awkward middle ground that a lot of AP exam stuff is, where the multiple choice questions are these really quick little things where you either kind of know it or you don't. And the open responses are this like, oh God, where you sit down for 15 full minutes and go through an entire derivation. Ideally a little quicker than I do it because you don't have to explain it. But that's just the nature of the AP exam. Goodbye, YouTube.